The flow diagram illustrates the three-step sequence in building a condition-based maintenance, or CBM, optimized decision model. I'll demonstrate all three steps. Following that, I'll show how to export the completed model to the corporate network, where it assumes the role of an intelligent agent working in the background to monitor condition monitoring data. In step 1, we'll build the hazard equation or model. The hazard model is also known as the Cox proportional hazard model, or PHM. It defines the probability relationship between age, represented by T, and the condition monitoring variables that the numerical procedure found to be influential to failure probability. Step 2 incorporates the predictive model, also known as the Markov failure time model. This step provides the remaining useful life estimate, or rule, R-U-L-E, and the confidence interval. Knowing the rule and confidence level assists management to make informed decisions based on probability as determined from the evidence. Step 3 incorporates the business factors, in particular the bottom line differential cost, or availability penalty as a result of failure, over and above the cost of preventive mitigation. So let's begin. Open the LRCM exact modeling application. The first step is to name the project and the failure mode or object part whose reliability is to be modeled. Let's take a moment to examine the data that will be used in model construction. The events table contains the age data. The table rows represent the sequence of relevant events that characterize each life cycle of an object part. The most important events are B, for beginning of a life, which is the age and calendar date at which the object part was renewed. EF, for a life's ending by failure. And ES, if the life ended by preventive renewal, called a suspension. Other event records in the age data that are known to have a reverse artificial effect on the monitored data are called non-rejuvenating events. In this case, the non-rejuvenating event is OC, which stands for oil change. The second essential table used for building the proportional hazard model, or CBM model, is the inspections table. It is a view of all of the available condition monitoring data. The numerical solution of the PHM finds which of those data variables are significant risk factors, and what should be the relative weightings of each of those condition indicators. Before running the computation, we need to use the application function that combines the events and inspections table into one virtual table. Once that is done, the algorithm will be able to step through all the age data in chronological sequence and detect any age and condition data patterns that correlate with past failure. Let's go ahead and set up the PHM computational algorithm. We'll name our model FEPB for lead and iron, but let's select iron and calcium as our first trial run. Dismiss the convergence warning, which is normal for small data sets, and examine the report. Check the column SIGN, short for significance, Y for yes, or N for no. Note that the shape, that is the age, and iron parameters are significant, but calcium is shown not to have any influence on failure probability. So let's run a second trial. Remove calcium and replace it by lead. Now all three parameters in the Cox-PHM equation are significant. This completes the first step in building the optimized CBM decision model. Next, we build the prediction or Markov failure time model, also known as the transition probability matrix model. We accept the ranges or bands that were selected by the software for each of the significant condition indicators determined in the previous step. This completes step 2 of the model building process. The third and final step introduces the business factors to be used to determine the optimal decision model. An optimal model is a balanced one. It is one that won't sound the alarm too often or unnecessarily, but in the same vein is not overly cautious. That is, it will not wait a dangerously long time before alerting the maintenance department of an impending failure. Assume that the mitigating preventive repair activity has a cost of $1,200. Also assume that the cost of the repair activity plus the penalty cost due to an unexpected in-service failure is $6,000. The observation interval is 250 hours, and the unit of cost is dollars. We can now examine the model's return of economic benefit. Here we view the calculated cost-risk curve. A report tabulates the cost and savings. The cost of failure is 38 cents per operating hour when adhering to the recommendations of the optimized model. The cost of failure, where no preventive maintenance is performed, is $1.53. The optimized model delivers a savings of $1.15 per hour, or 75%. There are many other tests within the application with which to further analyze the data and the model. When we are satisfied with the model, we export it to the network where it will act as an intelligent agent, automatically and optimally recommending timely preventive action by the maintenance department. The agent program runs at a preset interval, monitoring the latest data and issuing its findings into a database table that is accessed routinely in the EAM or CMMS. The table is an exception report indicating which failure modes of which equipment units have been flagged as being in a potential failure state. The remaining useful life estimates are indicated, as well as recommendations to intervene immediately or within a specified operational time period. The exceptions can be examined in further detail. For example, Unit 1779 has been flagged for immediate attention. The first of the underlying reports shows that the unit is in the red region of the graph, indicating the state of potential failure. The optimal recommendation is to intervene immediately in order to renew the failure mode in question, in this case, the transmission. The failure risk graph indicates a 15% probability of failure in the upcoming 250 hours, or a 30% probability of failure in the upcoming 500 hours of operation. The conditional distribution function shows, at the current moment, the rapidity with which failure approaches 100% certainty. The values on the graph are tabulated below the graph. Finally, the condition density graph estimates the remaining useful life. The standard deviation reports the confidence of the estimate. The table says, for example, that failure will occur between 4,000 and 4,800 hours with 99% probability. Incidentally, the confidence intervals shrink as our CBM program receives better and better age data from the EAM or CMMS as a result of a LRCM process. To review, we built our proportional hazard model, followed by our predictive model. This gave us the ability to predict residual life and confidence interval. Then we incorporated business factors to construct the economically optimal CBM decision model. Finally, we exported that model as an intelligent agent working in the background, examining data in various corporate databases in order to issue optimized maintenance recommendations. Thank you for watching.